Thank you, everybody. At first, I would like to say that I am not Sergei. My name is Dmitry, and I am Xinnor CEO. So we today will speak with Sergei and would like to present our ideas and findings about asynchronous I/O and some practical recommendations that we have for using asynchronous I/O in HPC workflows. Our talk will follow the next one about direct I/O, and I would like to say that this both talks doesn't contradict each other. It's just one is about one type of the scenarios, and the second one about different type of the scenarios. So Okay. Two words about Xinnor. We are a startup company from Israel, Silicon Valley, but Silicon Valley at Israel. Basically, we are located at Haifa, which is the motherland for a lot of storage startups. But we are relatively young, but we have a leverage of 10 years of experience in software rate design and mathematical research in this direction. What is our mission? We just developed the fastest software rate for NVMe, as we claim. But everybody shouldn't believe to our claims and can check it by your own experience. We are relatively young from one point of view. From another point of view, we have at the present moment a lot of customers using our solution. And one of our use case with a parallel file system, in this case, it was not Lustre, it was BGFS, was most innovative solution in last Flash Memory Summit. It was joint implementation with Western Digital and customer use case with BGFS. We just engineering company, very tiny sales resources and all the ideas about how to create a high performance rate. So what we do? Basically, we have two products at the present moment. First is Zero Rate. It's a software rate for NVMe, fastest in the world. And second one is a solution for HPC industry, which is called Z-Store. The story of this solution is very interesting. Yesterday, we had a lot of discussions in a party about how custom projects connected with the products. And I would like to say you that yes, it's connected. And our example with Z-Store, it's example of our cooperation with our partner, which is called Core Microsystems. It's a well-established system integrator out of Japan, which is on HPC business more than 30 years. And we are proud that we have a partnership with them since last 7 years. And the only reason why we are on a Lustre board is joint project which we started with them several years ago. And I would like to introduce today Mr. Ton Nguyen, who is our partner working for CMS here at the States, and you can ask as well questions not only for us, but for Core Microsystems as well. So, why we rely on Lustre? There are a lot of answers on these questions, and everybody in this audience has its own answer, absolutely. What is the answer for us at the present moment? Traditionally, as I told, we have started a project on HPC area, and we have a lot of implementation at the universities out of Japan. And our biggest implementation is Riken, where we manage more than 100 petabytes of data. But at the present moment, we see the new challenge for Lustre, and this challenge connected with cloud environments and with cloud managed providers which can use Lustre in the implementation. The main question at the present moment for such implementation, Lustre is very good in sequential, as everybody knows, and it would be much more better, as Patrick will tell us about direct I/O and all this stuff. The question is for clouds more about random, how they can manage great random workload results on the infrastructure. And the main challenge of our presentation and our talk today is to raise such questions in a Lustre community. For sure, we have our own answers and our own findings that we will present today with all the numbers. And I'm sorry that we will present today a lot of graphs, but it's important for understanding the subject area. And we would like to share all the graphs with all of you and all our numbers with all of you. It's not just a question of today's presentation. And I don't believe that in these 20 minutes, you will see and realize all the numbers. Everything will be distributed, and as much questions as you have, you can ask for us. So, why it matters? Because in a block layer, now it's possible to have great performance just from I don't want to say very small installation, but I would like to say compact installation. We just present last year at a supercomputing event a joint proof of concept with Kioxia. It's not actually a proof of concept, it's a joint project with Kioxia, where we utilize the server with the 24 drives, and that's it. And from this server, we can receive more than 300 gigabytes per second for sequential read, 150 for sequential write. And what is more interesting, for random, we can receive more than 60 million IOPS in read and 8 million IOPS in writes. So from block device, you could receive great numbers at the present moment. The question is how to pass such numbers to any file system and use it in a distributed environment. And all the findings that we would like to present today relates to our answer on these questions. So more specifically, what we will present today, we will tell a bit more about Lustre in a bit non-standard use case related to the cluster in the box solution. But this use case, it's not typical use case for today, but it would be, I believe, typical use case for tomorrow for a lot of cloud installations. In case if we, not Xinnor, by ourselves, community would find answer on the questions how we can receive great results on random performance, then it gives to us a chance to provide much more scalable installations for not only for cloud, but just for everybody who use AI workloads in their environments. And for sure, the solution will compete with standard SAN alternatives. And we will present today some numbers which we have in our lab. It's just not our lab, it's our joint lab with Core Microsystems out of Japan. So now I would like to invite Sergei to present all the numbers. And for sure, it's not our goal that you will remember all the numbers today. Yeah, we will share all the results, and we will have we hope that we will have your feedback on such results soon.
Hi guys, I'm real Sergei, and I was a guy who spent last year squeezing out such several million euros from block device. And when I came to our Lustre team and talked to them how we can get the same performance from Lustre, they didn't look happy because each year each new generation of hardware requires more and more efforts to get the maximum from the existing hardware, but we are still needed in some solution to provide our customers who need file level storage. And we tested different file system, but today we are focusing on Lustre and NFS over RDMA. We tested a couple of solutions. The first one is Cluster in the Box. Cluster in the Box is a solution which allows to have all Lustre server services in single chassis with HA capabilities, and we used only a couple of clients. In classic world, such configuration can provide us with several dozens of gigabytes per second for reads and writes, but today we are focusing on a smaller number of clients and small block IOPS. And the second configuration is virtualized solution. The problem of performance has two aspects. The first one is storage software, and the second one is application software, because we have been in Flash market more for the 10 years, and unfortunately we have seen that a lot of applications supposed to be storage hungry are not ready to take a deal with high performance, really high performance storage, and some of applications should be rewritten. And one of example is virtual interface implemented in virtual environment, which can be bottleneck, and we had to find some solution here. Okay, so let's start from briefly from hardware configuration. We had to SBB system based on Viking hardware equipped with AMD Milano CPU, and each storage node was equipped with single NVIDIA HCA, with 200 gig NVIDIA HCA, and we have 24 drives shared between two storage nodes. And the same configuration was used as a couple of Lustre clients. So I don't think these numbers surprise you. So we was limited. We started with IO test with DIO and buffered IO. So we was limited with 30 gigabytes per second per single client, and we was not satisfied with buffered IO, but we don't like buffered IO because we can control it. Buffered IO is mostly about client CPU performance and client memory, and we completely was unsatisfied with small block IO operation, because underlying rate could provide us with about 20 million IOPS for reads and 2 million IOPS for writes. So we started to find the way to how to improve the small block performance. So our performance engineering team having a deal with performance issues, usually investigate the system behaviors layer by layer. They start from disk drives and RAIDs and volume managers and virtual interface, LDiskFS, Lustre clients, and usually they use traditional tool FIO on investigating performance issues on RAID layers, on the device layers, and they found that using FIO with async, with AIO on Lustre client allows to reach the performance result much quickly. So we are going to talk about what we can get with AIO and utilizing some new approach. So some outcomes. So we can achieve the required performance on large sequential IO with existing approach using IO with DIO, and we have recipes, but we are still far away from block device performance on small random IO, and so it's time to look at AIO. So we utilized commonly used tool named FIO, and we did a lot of tests, a lot of measurements. We tested 4K random reads and writes with fixed num jobs and variable IO depths. We test the same with fixed depths and variable num jobs. We tried 1 megabyte sequential reads and writes, again with fixed num jobs and fixed IO depths. We tried different IO agents, variable settings, and of course, not all the numbers will be shown because we got several thousand of results, but we will show the most valuable numbers. And also we, of course, we did some preconditional for NVMe drives, and we filled in the file system volume to keep MDS busy. Some configuration description I will show 3 configurations. First one is optimized STOSS server without changing in client settings. The second one is client with max HPC in flight parameters set to 1, and the third one is client with max HPC in flight parameters set to 100 28. We saw no difference between lib.io and IO engines, so we will name both of engines as async. Let's start from single job result. And what is good, we see very good scalability on and we grow now when we grow IO depths, and it's not true. It's not fair to compare sync engine with async engine, because sync engine always works with key depths equal to 1. So we compared it with sync engine with increased number of jobs, and here you can see that sync engine with 16 jobs is equal to async engine with key depths of 16. But unfortunately, we found that sync engine does not scale with more number of jobs, but the latency layer is scaling up. So we see the same performance, about 150,000 IOPS, but as we grow IO depths, we see that latency scales linearly. And there's almost the same situation with random writes. Lustre client performance scales linearly, and with async IOs, and we see that the client with default setting performs a little bit better than clients with increased and decreased max RPC and flight parameter. So we recommend to keep it between 8 and 28 to get the best performance. And again, sync engine has a comparable results with 16 jobs, but it does not scale well with larger number of jobs. Okay, 32 jobs per client, and the results surprised me, because we were able to achieve performance layer close to 4 million IOPS, and I did double check. I run counters on my server side to be sure that all the data came from drives, and it's true numbers. We see that we can provide close to 4 million IOPS from very simple configuration consisting of single chassis, and we still have some room to improvement, but we tested a lot of open source distributed and parallel file system, and for now I can say that Lustre have the better scalability. Then I think it's the same situation with random writes, comparing async and sync IO, and having a client with default IO increasing key depths, we see almost linear scalability, and we are close to 1 million IOPS. So the second portion of outcomes. So we did it, demonstrated large block performance, but we see no difference, significant difference between DIO and AIO, and that's why we decided not to demonstrate charts. And on small block IO, the difference between AIO and sync engines reach several times, and sync engine scale well up to 16 jobs, and then sync engine stuck. And we were able to achieve about 50% for random reads and random writes from underlying array device, which is quite good, and it's still slower than utilizing the same configuration as a SAN storage, providing block volume over in-memory fabric, but the result is very good. And maximum effect, the performance is maximum affected by client parameter, which shows that max RPC in flight set from 8 to 24 shows the best results. Okay, couple of words about IO Uring. IO Uring has capabilities to avoid additional memory copies, to utilize polling for submission quiz and completion quiz, and to make some completion submission more lightweight, and running XFS over NVMe fabric with such options shows that we setting such options can increase performance several times, and utilizing more modern hardware based on PCI Express 5 drives, I saw that the total difference can be about up to 6 times. 6 times, I mean difference between IO with additional parameters and traditional libIO. But unfortunately, I found that Lustre client does not didn't demonstrate any performance improvement with additional parameters. I started my investigation, but it really required, I think, separated speech about because I collected hundreds of charts and I talked to our performance engineer, and so I will be ready, happy to share my results with community. So as again, IO-Uring with additional options provides significant performance improvements for XFS over NFS and does not work for Lustre. And for Lustre, at the moment, we see no any difference between IO-Uring and libIO. Okay, the second part of test was about comparison between Lustre over LDXFS and ZFS and NFS over RDMA server. We use the same testing approach. We try to mount NFS with different options. We try to change different parameters and choosing the best one. And so we saw no difference between sync and async mount option for reads, which is expected, and difference. And usually we saw no difference between different version of NFS server. Okay, again, we are starting from single job. Here you can see that NFS performs better, but you can see that NFS quickly reached the limit at QDEPs equal to 16, and for now looks like 250 or 300,000 IOPS is a limit for NFS server, both version 3 and version 4. And after we increase the number of jobs, you can see that Lustre still Lustre performance scarce linearly, and NFS stuck on performance of 250. 100 IOPS, and Lustre over ZFS without direct IO patch stuck on performance of 100,000. I'm not going to talk about a lot about sequential workloads, but let's see at random write with 4K, and the situation is almost same. NFS with async mount option is the fastest one, but again we reach the limit quickly, and NFS does not scale after 250 kiloIOPS, and Lustre still scale linearly, but the performance layer is a little bit lower. And after we increase the performance, increase the load, Lustre NFS reaches the limit, and Lustre is still scaling linearly. Okay, couple of thoughts about sequential workloads. So we see no large difference between NFS and Lustre over LDXFS for reads, and both for 32 jobs and for single job. But what is interesting, Lustre working when we try to Lustre with sync engine with 32 jobs is equal to async AIO with single job and 32 QDEPs. Lustre performed much better. You can see that. And the same situation for sequential writes. So NFS over DMA performs better with lower workload. I mean, number of jobs equal to 1, 2, 4, and for low QDEPs, but NFS over DMA does not scale well. It's stuck on QDEPs about 16, and Lustre significantly better as workload is increased. ZFS does not allow us to achieve the required performance with AIO, and I tried direct IO patch. I really like the direct IO patch because on sequential workloads it helps to get the maximum from hardware, but for small block I was not able to improve the performance. Okay, it's time to for Dima again.
Okay, thank you, Sergei. I see that we are limited by time. We have several other slides, but I think it would be intrigue with the questions about what we not to tell today as well. So from this point of view, I think now it's a good time to go to Q&A. Or maybe followed by the way that Patrick will tell about direct I/O and sequential workload, and we will have together Q&A for both sessions. Maybe it will be more interesting. So as you like, any questions now or after Patrick talk? Yeah. Okay. Okay, so thanks for additional time. We don't expect it. Yeah. So one additional finding that we have done. Maybe this picture is a bit complicated, but I will try to explain it in a simple way. So what we try to do, we try at first virtualize Lustre. It's done by virtualization of Lustre OSS. It's an upper layer of the blocks in this scheme. As well, we compare two different data paths. First data path was implemented at Linux user space, since we have our zero-rate implementation at user space on SPDK. And second implementation was related to the data path on Linux kernel. And we see something interesting. What is interesting? That for sequential, both approaches provide more or less the same results for read and for write. And it's about 50 gigabytes per second. But for random, it's absolutely different story. For random, we see scaling in user space of Linux, and we don't see any scaling for kernel. And is explainable by internal architecture of the kernel, and we can discuss it in a bit more, maybe not in a frame of the section, and further with the community. It's as well a very interesting discussion. But really good news is that we have a chance to achieve scaling for random, both for reads and writes. For reads, it's 4 million IOPS, and for writes, it's about 1 million IOPS. So it's more or less all what we want to say. I would like only to show some conclusions that everybody will have a full picture what we have presented. At first, our opinion that Lustre at the present moment, again, we are newcomers at the community. We are not as everybody more than 10 or 20 years here. But Lustre is a good solution for even standalone storages and can compete with SEN and NFS very well. And I think it's a possibility for some new use cases, not only for us, but for community as well. Second, asynchronous I/O greatly improve performance, and we can achieve it using our development of our rate engine. But there is a work that should be done by the community, and this work basically relates to improving I/O during support for Lustre. And we are open for this discussion with everybody, and we'll be happy to participate in this activity together with the community, because no single company can provide it by our own, it's for sure. As well, ZFS is very good solution. And it was presented today in many talks. But when it comes to scaling for small block I/O, LDiskFS should be used, and we don't see any other chance except use LDiskFS at least at the present moment. And the final one, but not least one, Lustre has very interesting use cases for virtual environment. And in this case, user space storage engines with a vHost controller implementation now can provide new perspectives for Lustre installations, and it could be interesting use case not only for cloud providers, but as well for on-premises installation. So that's all. Again, sorry that we take a bit more than was planned, but I hope it was interesting. Yeah. So we are happy to answer on all the questions. Now at the lunch, whatever, we plan to distribute all the slides to the community, and everybody can test by your own. It's better not to believe us and to check what we provide. Okay, thanks so much, and all the questions appreciated.
Any questions? Yes, one from Chris. Chris Brumgard, Oak Ridge National Labs. Just a small question. For your I/O U-ring tests, what kernel version did you use? I've been trying out some of the early versions of it and some of the early 5X kernels, and I haven't seen performance that good, so I was wondering.
Yeah, we used kernel version 5.14.
14?
14, yeah.
Okay, thank you.
Hey, Ellis Wilson of Microsoft. I had a quick question. It's kind of hard to see the slides, unfortunately, because of the podium from this angle. But I saw in one of the optimizations, or maybe a couple of them, checksums were disabled. Can you just comment on, like, roughly, obviously that's a slightly scary setting for some people to disable. Can you comment on roughly how much that improved performance relative to some of the other optimizations you guys made?
Yeah, about checksum, you say about it improved about, if talking about the highest load of 32 jobs with 128 queue depths, improvement was about 400,000. Sorry? Percent? 10%. 10%.
Thank you.
Hi, Andreas Dilger, WAMCloud. I see in your last bullet here, number 3, IOU ring features not working. I mean, we've tested just the basic IO, like from FIO, right? And so I know there's a lot more IOU ring options. You can do like metadata and things like that. If you have specifics about which IOU ring features are not working, it'd be great to file a bug report.
Yeah, so absolutely. As I told, it's only start point for the discussion.
Yeah, yeah.
Yeah, but you should understand that it's not one-way job, because application developer should also support the same features.
All right, let's thank our speakers again.